That's awesome. I mean, just have to also. Not any day.
All right. Hello, everyone. Thanks for joining us today for this DuraMAT webinar. This is hybrid, so please stick with us. We're both in the room and online. We got one presenter virtual, one presenter in person. My name is Harrison Dreves from the NREL Communications Office, and I have just a few quick housekeeping items before we get started. Just a reminder, everyone is going to be muted by default. You're going to be listening through your computer if you're online. If you're having any audio issues, computer audio works great for most people, but occasionally people have to switch to the telephone to get good audio. So don't be afraid to do that either by leaving the webinar or switching in the webinar. I will also be watching the chat the entire webinar. So if you're having any technical issues online, can't hear, can't see, have other questions, just drop that in that chat. That's that single speech bubble circled in green there. And I will respond to you. If you have a question, we're also going to be taking that using the Q&A panel. If you're online, you can submit a question at any point, and we will ask it when we get to the Q&A period. Michael, are we going to do one at the end of each talk or just at the end of the whole webinar?
At the end of everything? Yeah.
Okay, great. So we'll do a combined Q&A at the end since we have two talks today. For everybody in the room, when we get to the Q&A, just raise your hands and we'll alternate one online, one in person for the Q&A. All right. With that, I'm going to hand it over to Michael Owen Bellini from the DuraMAT leadership team, who's going to introduce today's speakers. And while he's doing that, John, if you want to get your slides shared, we'll hand it over to you after that.
Okay.
Thank you very much, Harrison. All right, so welcome everybody to the July DuraMAT webinar and seminar, because we have people in the room as well as people online. Today our speakers will be John Mauro and Mike Pilliod. John is from Penn State and Mike Pilliod from Central Tension. And since we started late, apologies for that, we were getting set up in the room here. I'm going to hand it over to John to get started. So thanks everyone.
All right, thanks so much. Thanks everyone for coming. I'm going to hold myself to, I guess, just 25 minutes at this point, and then turn it over to Mike, who will speak for another 15 minutes or so. And then we're going to have Q&A for both of our talks. So the idea here is that Mike and I are going to give kind of some fundamental background about glass science and technology with emphasis on some of the mechanical properties of glass. So I look forward to hearing all of your questions at the end and any discussion to come. So much of the human history can be defined based on the materials that have had the biggest impact on our technology and on our art, whether it's the Stone Age, the Bronze Age, the Iron Age. But a pretty good case can be made that we are now living in the Glass Age based on all of the various important applications of glass that have brought modern civilization to what it is today. And in fact, in this article in 2018 and at the Atlantic Monthly magazine, they called glass as humankind's most important material. And this year, in February 2024, National Geographic actually put the Glass Age on its cover. And if we think about all the different ways that glass has been a key enabler for modern civilization and for scientific discovery, it's common things that we take for granted. For example, with transparent glass windows that let in the natural light while keeping out the harsh precipitation and also providing a good thermal barrier between the inside and the outside. Glass spectacles for correcting our vision. Glass lenses that have been used in telescopes and provide, basically have helped to enable the modern field of astronomy, as well as glass lenses for microscopes and enabling the field of microbiology and the discovery of microorganisms and germ theory. There's also glass packaging that is used for pharmaceutical vials and for packaging of food. Right now, I'm actually communicating through very thin strands of very high purity optical fiber that is transmitting information at the speed of light. And that information is being displayed on probably, for most of you, flat panel displays such as TVs, computer monitors, smartphone screens, and all of these are made possible by glass engineering as well as the high strength cover glass that is on your devices to help keep the mechanical integrity of the devices. And of course, glass is ubiquitous in transportation, whether it is automobiles, planes, trains. It's very important to be able to see out of the vehicle while keeping all of the passengers safe. And so for all of these reasons, the United Nations actually declared 2022 as the official International Year of Glass. This is the first time that the UN General Assembly has ever declared an international year in honor of a material. So we're very honored that they chose glass, both for getting us to where we are today, but also because of the many possibilities that glass holds going forward in the future. But what is glass? Glass is a very difficult material to define. The official formal definition of glass is shown here on the left. Glass is a non-equilibrium, non-crystalline state of matter that appears solid on a short time scale, but continuously relaxes towards the liquid state. And we can see the meaning of this definition and also where glass comes from using this volume temperature diagram on the right. So if we start here at this point A at high temperatures and high volume, let's suppose this is the equilibrium state here. What normally happens is that when you cool a liquid and it gets just below the melting point of the corresponding crystal, then there is a thermodynamic driving force for the liquid to crystallize. It will undergo a first order thermodynamic transition, which involves a discontinuous change in the volume and the enthalpy and the entropy. And in order to stay in equilibrium, the liquid will crystallize, and then continued cooling of the crystal would lead to shrinkage following its thermal expansion coefficient. But, crystallization takes time. It takes time for the atoms in the disordered liquid structure to rearrange themselves into a crystalline configuration. For some liquids that have higher viscosities at their liquidus temperatures, it takes more time for the atoms to rearrange themselves into a crystalline configuration. And so for those systems, if you cool it fast enough through the shaded region so that the system doesn't have enough time to crystallize, then you get a phase which is called the supercooled liquid phase. This is not a thermodynamic equilibrium phase. The equilibrium here would be the crystal. But the supercooled liquid is just any liquid that is cooled below its normal freezing point. And this is what's called a metastable equilibrium, meaning that if you leave this unperturbed, it would stay in this configuration here. But if you give it enough thermal energy, it can find a deeper thermodynamic equilibrium by undergoing a phase change. Now, if you take this supercooled liquid and you continue to cool it, as the supercooled liquid continues to cool, the viscosity is getting orders of magnitude higher, meaning that the atomic motions are becoming slower and slower and slower. Eventually, those atomic motions become slow compared to the observation timescale on which you're observing the system. And when that happens, you undergo this continuous, what's called the glass transformation or glass transition process, which is a kinetic freezing in process because you're observing the system on a timescale that's becoming slower than the timescale of the actual kinetics of the supercooled liquid. So you get this gradual freezing in, and then in the end here, what we have is a material that behaves very much like a solid when it comes to its mechanical properties, but it has a structure that is very much like the structure of the liquid. And this is what we all know and love as the glassy state. So this is an out of equilibrium system. This is what we mean by saying that it is a non-equilibrium system. It is a non-crystalline system because it inherits the disordered structure of the liquid state. It appears solid on short time scales because if you say knock on a piece of glass, you're probing that glass on a time scale that is too fast for the liquid to be able to, or for the glass to be able to have configurational rearrangement. So it appears solid if you probe it on a short time scale, but on a much longer time scale, it continuously relaxes toward the supercooled liquid state because it wants to try to find its metastable equilibrium. So this is the formal definition of glass, and you'll note that this definition doesn't say anything about the chemistry of a glass. And in fact, in principle, any liquid could form a glass if you cool it fast enough to avoid crystallization. So that is really the key thing. Now, when we think about typical glass products here, and the strengths of typical glass products, they range by orders of magnitude. So many common glass products, like glass jars, for example, have typical practical strengths on the order of 14 to 70 megapascals. Freshly drawn glass rods can be higher, 70 to 140 megapascals, but if they're abraded, their strength immediately goes down to about 14 to 35 megapascal. Armored glass can be up to several hundred megapascals, glass fibers even higher. And if you have a freshly drawn glass fiber, it can be as high as 2 gigapascals. Now, if we compare the ranges of these numbers to typical metals, which are on the order of 140 to 350 megapascals, you see that glass is actually capable of being quite a bit stronger than most metals, but at the same time, many of the glasses that we commonly observe are actually weaker than many metals. And what is the reason for this? The reason, of course, is the existence of flaws. Now, if we go back to the original derivation by Orwan of the theoretical strength of a perfect brittle material like glass, this calculation is done based on not having any flaws in the brittle material and just calculating how much energy that it would take to break bonds to form new fracture surfaces. And if you put in typical values for a silicate glass, the theoretical strength of this perfect brittle solid would be about 35 gigapascals. So this is much higher even compared to what is observed for freshly drawn glass fiber. What compromises the strength of glass is the presence of flaws. These can be flaws that are due to the manufacturing process, but more commonly they are flaws due to the handling of the glass products. The original theory for the incorporation of flaws into the strength of a brittle material was done by Inglis. Inglis considered, what if we have an elliptical shaped flaw that is in the interior of the brittle material? So for example, this would be an elliptical flaw that has the dimensions shown here, and then being placed in uniaxial tension with an applied force. Inglis calculated how much of a compromise of the strength that you would get. And for example, if you take this, I know, perfect brittle solid here of having an ideal strength on the order of 35 gigapascals and introduce a flaw on the order of 50 microns, then this can actually lead to fracture at a dramatically reduced strength of about 35 megapascals. Now, the more common way of thinking about the reduction of the strength of brittle materials is due to Griffith, because Griffith is the one who introduced the presence of surface flaws. And in fact, surfaces of glasses or other brittle materials are what gets exposed to the environment. This is where we touch the glass. This is where it tends to undergo the greatest amount of damage. And so with Griffith's analysis, he based his analysis on basically the length of the tip, the length of the crack, as well as the sharpness of the crack tip. And this, in the denominator here, the square root of pi times c star. The c star is the critical crack length to induce fracture in a material. And this, if you take this square root of pi times c star, multiply both sides, this applied stress times the square root of pi c star is what gets us what's called the stress intensity factor, or K, introduced by Griffith. And the critical stress intensity factor, which now has a subscript C for K sub C, this is where the fracture occurs. And so this is given by the stress at fracture here, sigma sub F times the square root of pi C, which is the length of the surface flaw. The stress intensity factor has units of stress times the square root of distance. Typically, these are expressed in terms of megapascals times square root of meters. The failure of the glass or brittle material can occur in different modes. Traditionally, there are three different modes that are defined. The so-called mode 1 or opening mode, which is if you have a flaw as shown here, and then place this in some sort of uniaxial tension where you're opening this crack. And when mode 1 failure occurs, there is a subscript of this Roman numeral 1. So this is K1. There's also K2, which is due to mode 2 failure, which is a sliding mode. This is, as is shown here, if you place the material under shear, and that shear here is parallel with this plane that is formed by the fracture surface, then you can have mode 2 or sliding mode failure. And in that case, the stress intensity factor would have the subscript of 2. There's also a mode 3, which is tearing mode, which is shown in the lower right. This is if you have a shear that's acting in a direction that is perpendicular to that of the stress on this plane. And so we can have mode 1, mode 2, and mode 3 failure. What you probably most commonly see is this K1C. K1C is the critical stress intensity factor under mode 1 of failure. This is more commonly known as the fracture toughness of the material. So if you see the toughness quoted, that is the K1C, the critical stress intensity factor under mode 1 failure. For glassy materials, for typical silicate glasses, the fracture toughness is on the order of 0.7 megapascal times the square root of meters. A few other things that we need to keep in mind for the mechanical properties of glasses, especially under many years of operation, is stress-assisted corrosion or slow crack growth. And this, for silicate glasses, is governed by interaction between water molecules from the environment and the crack tip itself. Basically, water molecules can come in either from rain or from humidity in the environment. The water molecules come into the tip of the crack, which is under stress, and they will react with the silicate molecules at the crack tip. And when the water molecule interacts with silica, it breaks one of the bonds and the crack becomes one molecular unit longer. And so over time, water can propagate to the crack tips, react with the crack tips, and continue to make the crack tips longer. And this, over time, will compromise the strength of glass products. If this is occurring where the glass is under some sort of a constant stress or some sort of constant loading condition, this is what's called static fatigue, where the flaws grow over time due to application of stress. And what you see is that over time, the strength of the material is compromised because of the reaction with water and the progressively lengthened crack tip, or the length of the crack. This can also occur as dynamic fatigue. This is based on how fast that you apply load to the material. So if you're applying a faster load, you can observe a higher effective strength compared to applying the same load over a longer period of time, because if you apply the same load over a longer period of time, you're giving more time for water molecules to react at the crack tip, and that ends up compromising the strength of glass. And in fact, one of the famous plots here for the crack propagation velocity in glass is shown here on the right. This shows the crack velocity as a function of the stress intensity factor. And what you can see is that there are three different regions here. There is this region 1, which is a slow crack growth. This is where the crack velocity increases exponentially with applied load, as well as relative humidity. And so here you are limited by kind of how fast that the water molecules can react with the crack tip. In this mode 2, or this region 2 here, this is where the velocity is independent of the applied stress, but still depends on relative humidity. This is where the crack has become long enough that the kinetics are really governed by how long it takes to transport the water molecules from the outside environment to the crack tip, and then ultimately react with it there. And then once once the crack is long enough, we get to this region 3, where you can see there's a very sharp increase in the crack velocity with stress intensity factor. At this point, the stress intensity factor is high enough that it doesn't need water molecules anymore in order to grow the crack. So at this point, the velocity is independent of the humidity level, but still depends exponentially on the applied load. And at that point, that's where you generally will have complete failure of the material. Now, there are many different ways to measure the strength of glasses experimentally. Some of the common tests are shown here. That includes 3-point bending tests, 4-point bending tests, ring-on-ring tests, and the highly scientific ball drop test, where you drop a steel ball from various heights and kind of measure what is the probability of failure. And there may be other specific tests to align with certain specific applications, but these are some of the common tests that are done. So now that we know that glasses fail due to brittle fracture, we know that it's governed by the distribution of the sizes of the cracks, and we know that the strength of glasses can be compromised by the reaction with water. How can we actually improve the glass strength and toughness? There are several different ways to do that. One is to reduce the severity of the flaws. So how do we reduce the stress intensity factor K1? Another way would be having a coating to reduce the risk of surface damage. So this would aim to reduce the crack length, C. Another would be, how could we increase the fracture toughness? How could we increase the K1C of the material by crack pinning, deflection, or crack tip shielding? Or could we introduce some sort of compressive stress at the surface to increase the applied stress that's required to reach the sigma F level? So in other words, could we reduce K1, increase K1C, reduce C, or increase sigma F? All of these are pathways to improving the mechanical performance of the glass. How do we actually do that? One common way is thermal tempering. Thermal tempering is where you take thick, flat pieces of glass, subject it to a fast cooling where you can freeze in the exterior surfaces of the glass faster than the interior part of the glass. This pulls the exterior into compression. This has the advantage that it's fast. You get really thick compressive stress layers, but you really can't do this with thin glass, and you can't do it with complex shapes, and it also requires glass with a high thermal expansion coefficient, like soda-lime silicate glass. Chemical tempering or ion exchange has a number of advantages. This can be done on thin glass, like this is what's used in all your cell phone glass. It can be used for complex shapes. You can get much higher compressive stresses compared to thermal tempering. The disadvantage is that it's a slow process, and that means it's an expensive process. It takes on the order of 8 to 10 hours. Lamination can also be used. Ceramic is another pathway where you could turn the glass into glass ceramic to increase the fracture toughness, but you can compromise some of the optical properties that way. Fire polishing is a fast way to help reduce the severity of flaws on the surface, but it doesn't provide any additional lasting protection after that. Likewise, acid etching can reduce the severity of flaws, at least initially, but there's no protection later on. Coatings can also be used to provide longer-term protection, but that could also compromise some of the surface properties and the optical properties of the material. This is what a typical stress profile looks like for thermally tempered glass, where you can see there's surface compression on the exterior surfaces. So this is on the order of 100 megapascals of compressive stress at the surface. If you integrate all the compressive stress at these two surfaces, those integrated areas add up to match the integrated tensile stress in the interior. So all of the stored tensile energy here in the interior has to match that of the compression on the surfaces. Two of the key properties here are what is the magnitude of the compressive stress at the surface? Higher would be better. And also, what is the depth of the compressive stress layer? Basically, you're safe as long as the cracks do not penetrate through the compressive layer to get through this depth of layer and into the tensile layer. You can have glass fracture following different patterns depending upon stresses that get released. If you have a non-tempered glass like an annealed glass, the cracks will propagate out in straight lines. So this is all the energy because of the initial impact, but the glass is not releasing any more tensile energy, and so you don't get any branching after the initial impact. With tempered glass, on the other hand, if the crack penetrates through this depth of layer and into this tensile regime, now the glass wants to release all of this tensile energy. The tensile energy release causes the crack to accelerate until it hits the terminal velocity, which is governed by the speed of sound in the glass. At that point, it still wants to release energy at a faster rate, but it's unable to travel any faster. So the way to do that is to bifurcate the crack. So one crack splits into two cracks. They continue to release the tensile energy, continue to accelerate until they reach their terminal velocity, and then they will branch again. And as a result, the pattern that you get from tempered glass failure is these very small shards, and this is what's called frangibility. And this is because of the release of tensile energy. The most famous example of this is the Prince Rupert's job. This is an extreme example of thermal tempering, where it's extremely strong here in the main part, but if you clip the tail, this will basically go into dust upon fracture because of the very high levels of tensile energy. Tempered glass is very effective at improving the practical strength of glass. This shows the practical strength of tempered glass versus annealed glass, where you can see some major advantages. Very quickly, another approach for improving the strength is through laminated glass. The most common way of doing this would be like in an automotive windshield, where you've got a polymer layer in between two glass layers. But another common way is actually a glass laminate. You probably have some of these dishes at home, these Corel dishes. These are just laminated glasses. So there's an interior glass, which is white, and this is coated by a very thin, clear glass layer. And what gives these dishes their strength is the difference in the thermal expansion coefficient between the outer layer and the inner layer. This can also be done in flat glass forms. And in fact, one of the projects I worked on for a number of years at Corning was this double fusion draw process, where you've got one glass that's being melted up above, another glass down below. The upper glass flows over the inner glass, and what you get is a 3-layer laminate at the bottom that automatically gives you strengthening based on the differential in the CTEs between the clad glass and the core glass. Toughening due to glass ceramics is basically growing crystals in order to deflect cracks. So this is a very effective way to improve fracture toughness. This is what makes Corningware work, for example. And of course, we have ion exchange. Ion exchange gives you the highest level of compressive stress. This involves taking the glass, submerging it in a molten salt bath at a temperature of about 400 degrees C. What happens is that the smaller ions from the glass, like sodium, will diffuse out into the salt bath. They get replaced by larger ions like potassium from the salt bath. The larger ions want to expand the glass surface, but they're unable to because the interior of the glass is keeping them within a certain geometry. And so this concentration profile of potassium gets converted into a strain profile, which gets converted into a stress profile. And this gives stresses on the order of about 1 gigapascal. So it's much higher stresses compared to thermal tempering. The stress profile follows this complementary error function, which basically follows the diffusion profile of the potassium. And this concentration profile here of the potassium gets converted into a strain profile by multiplying by this factor B, which is called the Cooper coefficient or the network dilation coefficient. This tells you how much strain that you get per mole percent of ions exchanged. And then that strain gets converted into a stress profile by multiplying by the Young's modulus over 1 minus the Poisson's ratio. And so you get a profile that looks kind of similar to the shape that we had with thermal tempering, except you tend to have a lower depth of layer and a higher compressive stress. So it gives you kind of more strength to your armor, but the armor isn't quite as thick compared to thermal tempering. I'm going to go ahead here And just mention that one last thing is what's called a native damage resistance. This is something that we invented at Corning. This was commercialized as Corning Gorilla Glass 3 with native damage resistance, or NTR. And basically, this is another way to improve the practical strength of the glass by actually introducing a plastic deformation mode into the glass, where you can see this is an older glass under an indentation or under scratch compared to a newer glass under the same indentation or scratching conditions. And with this native damage resistance, this improves the resistance to cracking by about a factor of 3. So it's actually a pretty big deal that is used on a lot of smartphone covers right now. So if you want to learn more, I've got a couple of books. There's our glass book, Fundamentals of Inorganic Glasses, and the Kinetics book, Materials Kinetics. But I'm going to turn this over right now to Mike. So I'm going to stop sharing, and all yours, Mike.
Great, thanks, John. About the guy who actually wrote the books on glass science. It's always good to know people in the world. Actually, John's the first guy I gave a talk at PVR, the photovoltaic conference Michael put on, and one of the outcomes was just to do a glass webinar. So John was my first call. He's like, it's great to know people in the glass world, and so now he's in the network. John jumped right at the opportunity to present to you guys and help out. So thank you, John, for that. So for those of you who don't know, Michael Pilliod, Central Tension is my company. I represent myself in the glass kind of product development world. I spent years at Tesla doing glass development, and before that at Apple. John and I crossed over at Apple, and was fortunate enough to go to school with John. Started my career at GE. I gave this sort of talk as far as like you get the sort of simpleton version, but I've spent most of my life on the on the scale of processing, manufacturing. So all the things we do to screw up the strength of glass that John just talked about, and to make a part. I'm going to focus my talk today primarily on the toolbox in the middle versus the driving force and in-use handling stuff and lamination side of things, mainly just on speed, as well as to give the team enough time for asking questions. Within the top, there's a bunch of, the glass world's awesome and huge, but to make it sort of within the current pattern soda lime glass that's thermally tempered and edge ground, the sort of these areas around breaking down things into rule of threes, as well as to start with pattern glass, edge profile to put an edge condition on the glass, thermal tempering, and then lamination side of stuff. So rolled glass, just to start with, you take the soda lime silicate that is used in PV glass today, melt down the sand, and they literally put it through two rollers or 3 rollers to put the pattern into glass. So you go from a melt touching the surface of metal, and then comes out into pattern glass. So pattern glass was invented before the float process, before the fusion process, to make kind of like even sheets of glass. It's ubiquitous in the PV industry. There's people who do float glass and make modules, as well as thin film technology. But from the crystalline world, pattern float glass pattern soda lime glass is the tool we're using right now. And there you have composition, thickness, and surface quality that I'll chat through. And then float and drawn glasses are other mass manufacturing techniques. Float being primarily used in architectural, automotive, and then drawn glasses, like in your cell phone thing, of more of a pure glass surface. And any of these topics we can dive more deep into for timing. For edge and profile, you take glasses done in sort of blocks or mother sheets, so this long continuous giant sheet of glass. You then take it and scribe and break it into smaller pieces, and then do an edge profile grind on your thing to make your profile or your edge profile. And that's done with a grinding wheel, and there's no sexy version of it. The glass goes through and you're literally grinding the profile. So we'll go through the edge conditions, but if you want a circular or kind of a bullnose edge, your grinding wheel looks like this. If you want a bevel, your grinding wheel looks like that, and you literally grind that edge into the surface. But there you have profile, perimeter shape, that'll talk a little bit around corners, and then process control around how often do you change out your grinding wheels, how obsessive are you around edge quality shipping. For thermal tempering, we'll go through a bit of the thickness controls, anisotropy, which is that word for stress, differential stress within your part. And then the edges and corners aren't getting enough love right now, with kind of blinders on about what would be relevant. Feels like edges and corners are a pretty big deal, and they don't get that much love in thermal tempering. And then there's module lamination, which we don't get into today, maybe other sessions. I guess one of the goals of the day is to introduce you to people in glass world and set up a second date or a third date, my opinion, to get with you guys in your world. But there you have interlayer material, asymmetric glass things, so thicker outer glass, thinner inner glass, and then corrosion mitigation, so things like edge sealing. That's it. Within rolled glass, so this is like my research intends to be YouTube videos and early morning YouTube videos. So there's a great YouTube how it's made pattern glass. So if you want to watch it, the link's there. You go through melting it down, but you'll see how quickly it goes from the molten state through metal pieces that imprint the pattern onto the backside of your glass. These little dots that I'm still searching for a reason why they're there, just to be honest. But it does create that sort of any sort of like structural glass that's in there. If you look at like patterned shower glass or architectural glass and glass, will tend to go through this patterning process. Embossing as well, if you have leathers or papers, similar type of process. It then gets cooled down and made into mother sheets there, but worth a watch just because it gives you a sense of like, when we look at this from a glass perspective, hitting metal so quickly is just scary. You're cooling it down really fast. You're inducing a bunch of interactions between your metal drum that you're imparting your rollers on and the glass surface. So from a surface quality perspective, the best glasses you can do when John was explaining the fibers or a fusion drawn process is if it can just hit air and cool down on its own, you have a perfect surface out there. If you touch it with anything, rollers, float, tin, you're going to impart damage onto the surface of your glass. And this is teeny damage. This isn't visual damage. You just need little teeny flaws that are in the surface of the glass to impart damage. But the reason it's used, just why are you using it? Just for things, pretty easy to industrialize, fairly cheap process to make. You can become a glassmaker really easily this way versus building a float plant or doing a fusion drawn plant. But here's sort of the breakdown of like, start off with like my cartoons here. You start off with a big mother sheet or block of glass, and then you have to take a diamond, typically a diamond scribe. You scribe a line, snap a piece of glass into your fairly rough geometry of an XY piece. And then you edge grind profile it. So if you're going to put on sort of a pencil edge or a beveled edge, it'll go through that process to create the perimeter final shape. You go to thermal tempering or strengthening and then lamination. And there's sort of like decorative rolls that are done in glass to give you a sense of like, it's the same type of process. It just becomes more like on the solar glass, you'll have little teeny bumps that are on that roller. When you look at sort of edge profile, and again, this is a quick snapshot and what I did to sort of get ready for this. There's a whole bunch of other edge profiles out there. The most common in architectural are this sort of like kind of a knocked off edge, sort of polished thing of a small little chamfer. If you see any architectural exposed glass edges, you'll tend to see this edge profile, typically polished for reasons for aesthetic, some strength. But the grinding wheel there is sort of in a linear fashion. You can see sort of in those grinding wheels, the glass goes through and it hits up a bunch of different grinding wheels that put in that profile that you're looking for. And there's sort of like pencil edge, you'll hear bull nose, but basically it's a big rounded edge is the strongest edge, if you will, because you're not putting that glass in tension, you're also having any sharp corners. Things that you have to watch out for there are like when you're grinding the wheel, the grinding wheel is also going away at the same time. How well your glass is attuned to the grinding wheel, if it's up high or down low, you can get chips on that surface that's right there at the transition here. From the flat to the edge right there, you tend to get radial chips at that thing. So little teeny, just like a scratch that John showed, similar to that, where you'll see sort of like little digs, look like a little rabbit, like kind of ate your side on a microscope. Those things are all flaws that are just ready to cause damage in the field or breakage in the field. But when we approach sort of like, if you look at like how to quantify that things, most of them, there's a bunch of light aspects. There's how like surface roughness, mostly it's looking under a microscope and taking a look at it. Edge conditions tend to be mostly driven by like kind of 3-point bend tests to get a sense of like how strong is my edge inside of that world. But when it comes to the corner, you end up in a bit of these tend to be inline processes at scale. So you're sending your glass through one direction, flipping it 90 degrees, sending it through the other, and the poor corner just is off for the ride. So likely if you look at your solar modules, you'll tend to see a weird looking corner inside of that. And it means sort of like you put in a curve and a curve, but when they end up at a 90 degree, you don't, unless you surface profile the whole thing with like a cam and follow CNC, you don't finish that edge in a way. So you're likely in this sort of like this dubbed corner aspect, but even worse, sort of non-controlled of like you end up trying to surface those in both things. You end up with like a little chip there or a sharp corner, which we'll talk about later. When you thermally temper, it's a little bit scary when you end up with sharp corners. From a like, you know, if you looked at like making the strongest module, like you look at like the iPhone's not designed this, so that's more aesthetic as far as the curve goes. But those curved edges would do helpful, especially in bending moments and when we get into tempering, about how it is a temper and what's the stress profile in that edge. Things to watch out if you sort of like, I guess like audit your supply chain, or if you're going to dive in deep to like people making solar modules. It's more about sort of probably more about a feedback loop. A lot of this is optical inspection. People look at the glass to see if it's okay or not okay, put under a backlight pieces of glass. But there are other sort of quantitative techniques that you can look at there. But this is the thermal tempering profile. And when you get thin, it gets scarier. Right around 2 millimeters, you come around the theoretical limit of quenching. For those of you who weren't at the talk, this is basically the quench pressure versus glass thickness curve. And with the drive from like 3.2 to 2.5 to 2 millimeters, the way thermal tempering works is you heat up the glass, you freeze the surfaces, it shrinks in the middle, and it pulls the surfaces into compression. You need a certain amount of thermal mass to be able to pull the surfaces into compression. So when you freeze the surfaces, it gets harder and harder to do. Your quench pressure has to go up and up to do it at thinner modules. This is why it doesn't work with thin glass that John mentioned. But what it also does is it typically in thermal tempering, these are polarized light scans of long rectangular glass and also things with holes in them and corners. This is my like, John has a bunch of like equations. I just have color charts here to give you a sense of like where the problems may be. In this world, you're looking at the polarized light, you're looking at differential stresses in your glass pieces. Thermal tempering tends to be done at the bulk level. It tends to be done in the middle of the glass. You're tuning in to put a stress profile and a breakage pattern in the middle. But if you could imagine cooling down a part, your surfaces, your edges are also cooling at the same rate, and you get a ton of stuff going on around edges and corners. And this is sort of my comment that edges and corners would need a little bit more love in a rectangular thing that has a lot of edges. Also, if you put a hole in the back glass, when you go to thermally temper it, your stress profile is going to look bizarre around the hole. It's going to mean you have differential stresses, and that tends to be a place where glass is not so happy when it has a bunch of different areas that's bottled up in those areas. There are a bunch of ways to measure it continuously polarized light. This will be at the single glass. This tends to be mostly in transmission. So if you do this before you laminate an opaque solar panel, this is probably the place to do this would be right after the cut and grind and final edge finish. There's a bunch of polarizers that can do edge finish as well as things, but then mass manufacturing ones that can do it on big scale, large architectural glass. The reason they do this in architectural glass is people didn't like to go by building big skyscrapers that have differential patterns or waviness or put polarized sunglasses on. That's why a lot of this was developed, but solar could take advantage of that scale. Be able to do that. The way they measure, a lot of the ways, the kind of old school ways they measure thermal tempering is they do it by a breakage pattern. They take the piece of thermally tempered glass, they put a sharp point, break it, and then they collect and weigh the fragments and see if it's tempered or not tempered. And that's kind of the more traditional way that you can measure the stress profile, but online in a production environment, that tends to be the way that it's done, with the operator tuning the pressure and quench pressure to give you the right breakage pattern. There's definitely an app for that. There's a couple of places that you take a picture and it can measure these areas. I'll put a link in the description, but it still takes your breaking the glass, doing the format. And this is in my opinion, a bulk measurement. This is taking center mass, you collect the things. It doesn't focus on the edges. Now that beautiful stress profile with the compressive stress on both sides and this central tension region, when you get to an edge, you likely don't have that beautiful stress profile because you're cooling all around this edge. The edge gets a lot of thermal energy cooling this way, so it drives in this area. You tend to get this little keyhole looking thing that's at the edge of the glass. This happens also in annealed glass. When that glass cools down in automotive, you get a little bit of a tensile region around the perimeter, about 100 millimeters there in automotive. It's probably lower here, but it does create an area where you have a lower compression area inboard of your edge, which would be scary, and especially more scary when you go thinner, because you have less safety margin, and you could more than likely that exists in thicker tempered glass. You just have a thicker compression layer it's buried under, so no one really cares that much. As you get thinner, this will become more pronounced, as well as things around like holes in junction boxes, corner profiles. But this would be a little scary in that way of how to quantify the stress profile on a thermal tempered perimeter and areas around holes. It's doable, but as a quality control metric, it's unlikely that PV solar module threads are quality controlling or developing towards this. My estimate would be that. And then this is based on sort of these things. I think it's definitely modelable in a way that the most modeling in thermally tempering is not been that. It just hasn't gotten enough love, because in architectural it's thicker, 4 and 5 millimeters. Anybody can thermally temper. It's really good, it's cheap, and it works. As you go thinner, science might need to take over a little bit more push towards quantitative techniques, as well as other strengthening mechanisms that would be helpful for this. But it's just sort of a picture. There is sort of work that's done, but it then comes off. If you look at an annealed glass, you'll see high stress points. And especially as you get larger modules, this thing is shrinking basically to pull in stresses. So you have a bunch of inner stuff that keeps shrinking. It's as the larger you go, the more distance you have, and it sort of pulls this thing to corners. Now, it's not pulling it, and your module doesn't look curved, but it's not happy. The corners are just not happy in that world. Same things, a bunch of books on that, and then some of the lamination techniques that we talked to. I want to leave enough time for questions, but thank you for offering things. I took a tour around your guys' national lab up into South Table Mountain, so I love being here. So I appreciate the time, and yeah, let's open up for questions. And
excellent. All right, thank you so much, Mike and John. Appreciate that. So I'm going to take questions. I'm going to try and alternate between the room and online. So if you're in the room, just raise your hand, and I think the room mics should get people. Is that right, Harrison?
They should pick people up, yeah.
Okay, so just raise your hand if you have a question in the room here. I saw one in the back first.
Just curious, you said when you grind the edges, what are you using for abrasive?
Yeah, typically they're diamond impregnated abrasives, so very similar to a grind wheel that's out grinding anything. So they tend to be diamond impregnated with resin that are shaped in the profile. Yeah, and those go on to sort of CAM CNC or direct in line. But it sort of would be in a disposable commodity.
Salil?
So what controls the depth of compressive stress glass? How do you control it? I'm assuming you would want it more.
This might be a John question.
So for chemically strengthened glass via the ion exchange process, it depends on how long you ion exchange it for. So basically, it depends on the depth of penetration of the larger invading ions like potassium. So you can go to longer ion exchange times, you can go to higher ion exchange temperatures, or you can try to design a glass that has a faster diffusivity of the alkalis, and there are pros and cons to each of these. If you go to high temperatures, you can also relax away some of the stresses. With thermal tempering, you don't really have control over that because it's just governed by Fourier's law with the heat transfer. So it's always going to be 20% into the surface of the glass. And for lamination, that crossover is just governed by how thick the cladding is compared to the core. And the crossover would occur where you've got the interface between the cladding layer and the core layer.
And I would also say you can over strengthen a piece of glass and make it unstable. If you drive too much compression stress in the surfaces, that balance that John was talking about, you don't want to mess with the balance, or you end up with a fantastic breakage, a little bit unstable.
So Henry Hieselmeyer online, he says or asks, regarding moisture corrosion of glass, can you say something about what you expect the long-term mechanical strength of PV module glass, PV module glass in the field? How does one ensure 40-year glass life with variable mechanical stresses?
So yeah, that's an important question. So I mean, in order to try to improve the long-term strength, you can have compressive stress layers, which are always going to be helpful in protecting against that. You could have a coating that would be hydrophobic to help prevent the moisture from getting to the glass surface. You could try to design the modules to reduce the amount of stress that is going to be experienced by the glasses. You could design your compressive stress profile to have a higher compressive stress at the surface. All of these are tactics that can be employed to help improve the longevity of the glass products. But we'd have to study what conditions it's going to be exposed to, both mechanically as well as what humidity is going to be in the environment, rain. Of course, hail will give you mechanical impacts, which is going to compromise the long-term strength as well. So all of those are factors.
Yeah, I think also that one of the great things about having John here is that he definitely will ask questions like there's a lot of weapons you could have against like hydrostability of glass. You can do different types of glasses that are out there. We'll tend to ask a lot of questions around scale, cost. You've already heard John talk about chemical tempering. It just costs a lot. So you have a good ally here who knows the stuff. There's a lot of weapons against these things, but also some more practical ways that you could solve some of these issues that you have.
Okay, so a question from Billy Stanbury, or more of a comment, I suppose. So I did not think most cover glass was patterned, rather than tempered flat. And I thought the hail impact strength of patterned glass was much lower than tempered glass. Is he wrong?
I think it's a little bit of nomenclature here. When we say patterned glass, that's actually making the glass sheet. So the processes there are rolled and patterned glass you may put in the same category, float glass and like a drawn glass things. Tempering is a strengthening profile. You can temper patterned glass, float glass, or fusion glass as long as it's thick enough. So those are two different aspects. I think the sort of the hypothesis here, if you will, of why patterned glass would be less impact resistant than float glass is surface quality. You've induced a whole ton of surface defects by patterning your glass. Like there's zero doubt about that. It's just whether the magnitude counts and how much the thermal tempering has like kind of blanketed those defects. But bumps and defects, you may consider those the same thing in the back. So it could be good. Like one thing is just quantify what the bumps give you, if anything, and then what is their effect on impact resistance relative to more of a pristine glass surface type of thing. But there's a lot of evidence out there. In my preferred method of glass breakage, which is throwing steel balls at glass and seeing if it breaks. So,
John, any comment on that one?
No, I think Mike covered it well.
Okay, perfect. Question online from Ian Hahn. So you mentioned the technical challenges for tempering glass below 3.2 millimeters. What questions should module manufacturers be asking their glass suppliers to ensure claims of 2 millimeter tempered glass are valid? Sorry, to ensure claims of 2 millimeter tempered glass are valid.
Yeah, I think my sense is it's probably more like an auditing thing here. It's not impossible. Like you're not in the impossible realm. You can do this, but its processing point is very, very like limited here. There's not enough of it's not dummy proof anymore. It's really going to take high-end equipment, process control, quantification, and full out auditing of like how do you keep glass like makers honest about not chipping out on anything or trying things. It's not that they want to make a lower part glass, but they're, if it's energy usage and the flange pressure takes energy, they may tune it down a little bit, not knowing that it affects the overall profile. But I think as you get, my sense is you're in a realm here that hasn't been that well explored, to be honest. Like, how do you temper 2 millimeters? Because most people are tempering well above 2 millimeters. So maybe it just hasn't been looked. It's been looked at to some of the equipment manufacturers, but they're going to need new tempering lines, they'll need new quality control aspects. In addition, like you want to look at the whole surface of the glass and might comment around holes and corners and edges. Like those are important, as important as bulk, but just don't focus on the bulk. That would be my suggestion. But yeah, you want a team of auditors out there.
Sure.
Yeah.
Yeah, and it's not really a question of can or can't, it's really how much. So you can, take any flat glass of any thickness and put it through a thermal tempering process and get some level of compressive stress. But the amount that you get depends on the thickness of the glass, it depends on how fast you quench it, it depends on the thermal expansion coefficient of the glass. So all of those factors enter into it, but it's better to think of it as in terms of, how much compression you get.
Any questions in the room here? One in the back. I saw the first one.
Yeah, good question. So I do chemical analysis on solar cells growing up glass, and then if you look at the glass, you see obviously silicon, oxygen, sodium. You also see other things in there like calcium, magnesium, etc. What do those do? Why are those in there?
So that's just standard soda lime silicate glass. The calcium and the magnesium need to be there in order to stabilize the glass structure against crystallization. They also help to improve the resistance of the glass to attack from water. If you just had pure sodium silicate glass, it would be very readily attacked by water. You would not like the performance at all. There's also a little bit of alumina that's included, and that also helps to improve the durability of the glass, the resistance against crystallization, and the strength.
And given that you have a lot of glass makers, it's very likely that your composition of soda lime is not controlled in that well, as far as they want to make the glass and make it into things, but it's very likely your flavors are there. And then you have things called fining agents, where it's probably where the antimony is used, or things to get rid of bubbles. So there's some there just to get what they call fining agents in glass. And that's the most logical approach to apply antimonies in glass, I think.
Yeah, and I put this in the chat too, but I'm actually in the process of putting together a whole introduction to glass science course that covers all of this stuff in great detail, all on YouTube. I dropped the link to the playlist in the chat, so you're welcome to check those out too.
Yeah, that's awesome. I saw some questions in the chat asking you to go into more details on some of the concepts. So it's good to know that you have that coming. I saw more questions in the room.
Yeah, so just quickly, how involved are you all with architectural type stuff? We've got a program here on durability of glass units for architectural, really specifically around emerging technologies, did a lot of work around electrochromic, doing stuff on thin glass units right now, and then also a large study on vacuum insulated.
Yeah.
If you're into that space, I would love to talk.
Yeah, absolutely. Yeah, it's always been an intrigue. I spend most of my life in product companies, uberly focused on consumer electronics and automotive and some solar, but architecture is that's the monster that runs the glass industry. So yeah, it's great to chat about it.
Right, and here at Penn State, we have a new institute called the Cocco-Ziello Institute of Real Estate Innovation, and the first thrust of that is on building materials, and that includes glass for architecture as well.
Nice, very good. Well, you've also got some of your students and you're collaborating with some of your other buildings people now.
Yeah, John's built the largest glass technology group in all of the United States, and built it up pretty much from scratch. So we'll plug for the team there, as well as the network that you're involved in. I think
Thanks, Mike.
there's Glass Worlds. There's a bunch of people that are willing to jump in.
Excellent, good job.
I think we can do one last question, Ashley.
I have maybe two quick questions.
Okay.
For the first quick one was, how standard is the polarization screening technique? Is that pretty, you got a glass line, you use it, or is it pretty?
It tends to be, it's a non-destructive one, so that's nice, but it tends not to be, in my experience, it's not used that often. It's more like, I got a problem or things, maybe in some higher end aspects of it, but it tends to be a non-destructive, are we okay or are we not okay? Actually, I think it's it could be extremely helpful inside of these things. And then high-end architecture is using it as a quality control, basically to get rid of those ripples. But to be honest, I think Apple stores are probably one who's asked for it mostly, just so they don't have a lot of tempering hot marks and things like that. Yeah, but it for sure is on, I think that it's also a level of you have John will know more about this, but you have like an optical factor you have to put in for these aspects. So you need to, there needs to be some material level work as well as things. So to answer your question, I think the people doing it if you put a polarized filter, you can get the pretty pictures that I have. The quantification is another aspect, which it's doable. It just takes some standards, stress lines, and other things that.
Yeah,
But I
so
also
the-
think it could be super helpful with just quantitative of tempered glass in general. But John.
Yeah, so the material property is the stress optic coefficient, and that will depend on the composition of the glass too. The stress optic coefficient tells you how much birefringence that you get per amount of stress too. So that's what you need to know in order to take kind of the qualitative observations to quantitative levels of stress.
All right. Well,
I can ask the,
yeah. So Mike's going to be around,
Yeah, I'll be around
for the rest of the day, so he'll be free to chat. And for people who want to ask questions who are online, I'm sure John or Mike will be happy to take questions by email.
Yes.
So once again, let's thank our speakers, John and Mike. Thank you very much. And we'll
Thanks,
leave it there. Thank
everyone.
you.
Take care.